if you had a chance to look at the previous slides, and nevertheless, they will become a course. They will become an entire course on offensive security very soon, where I describe a CPU interpreter from scratch in Python, okay, which is disassembling an assembler that we define. So we do everything from scratch. Now the jump here into JavaScript is that because JavaScript is indeed another interpreter, it's indeed a virtual machine, and that is why we will use it to actually explain the first primitive, which is addressOf. AddressOf actually means, okay, sorry, this is nice for a live. So addressOf means by the end of this talk, which will be approximately 1 hour, we will be able to use a primitive, which is an exploiting primitive of JavaScript, which is called addressOf. So which means leaking the address of an object. But before getting into that, we really need to go step by step. So first of all, I have to say thank you to several people that I don't know directly, but I've greatly benefited from their medias and videos and explanations. Nonetheless, I have created my own version, which is, let's say, less synthetic, and also uses some C and C++ examples to give you a better sense of how these kind of vulnerabilities happen within the JavaScript interpreter. Okay, so we have Linus or LiveOverflow, which is very well known, Niklas, and also I normally use Claude for coding because it really somehow matches my style of programming and low-level stuff. It's not perfect, but well, it helps. So I actually prepared the Docker for you guys. You can get it. It's called jscsploit from the Docker Hub, and it contains basically the material. And the difference with what LiveOverflow does is this version of the WebKit is compiled for Linux, and it's available in Docker. So somehow as I said, I created a twist of it. So if you have time, I'll publish the slides, so don't rush it. Enjoy the live for today, then you can reproduce everything as we also record the meeting. Okay, so the idea is you get the Docker, then there will be some environment variables that are actually helpful to debug a little bit when the interpreter is executing. And we will understand where and why the virtual machine is applying optimizations to the code as a compiler. And I have some examples to like using binary ninja to actually explain you exactly what it is. And then we'll go into what is hot and why the hot functions are actually transformed by the interpreter with optimization, which could actually get into these 3 levels, which is the base jitter, the data flow graph, or the faster than light FTL mode. So there are transformations on code that will make it basically faster. And then there are also countermeasures, because when you make it faster, so when you actually bet on performance, you will give up some security. And the solution they have when something they are not sure about, it's clobbering. So it's a function you can call in the JavaScript interpreter when you are not sure what is going on with your data and you want to clean it up. And we'll see how the types are actually checked through our mocks in C and C++, and then we will look at the final implementation of the first primitive, which is addressOf. Okay, if you have any questions, I recommend you write them in the chat, raise your hand, just notify me if you like, or just sending it in the chat. I have it on another screen, so no big deal. You can send an emoticon or whatever from time to time, and I will ask you to send me some feedback to clarify and do not lose the thread myself. So the video will be full of demos and tests, so you can also ask for extra clarifications. Okay. As I said, here we have a Docker, so you feel free to download it, which already contains the debugger. It already contains the code of the interpreter. And if not, because now I'm just remembering that there may be some issues with the mapped volumes. I think they will not be problematic, but maybe if you have some issue, let me know, and I will copy back the data on it. Okay, so let's start. First of all, in order to control this interpreter, you can either enable or disable all the optimizations. You can disable the first, the second, or the third level of optimization. And you can also enable disassembly, which is you could see how the JavaScript code is actually transformed into bare metal assembly for our CPU. If you actually followed a little bit how we introduced QEMU, this is very similar. I mean, QEMU is a jitter and is actually transforming machine code, for example, ARM, into x86. If you compile QEMU for x86, but is QEMU ARM, it will read ARM code, and it will transform it for x86. Now, if you have the Java virtual machine running in your browser and your machine is a Mac, JavaScript will be translated into ARM code. If your machine is x86, JavaScript will be translated into x86 code. And this is no different from our simple processor that we had written in Python. For example, this is a very simple program, and the first two instructions, they are basically used as bytecode. They represent the operand, the operator, and this is a load immediate of the value 0 in the first register. Okay, so you here have an example, and there are the slides online if you want to take a look. In principle, also JavaScript language patterns can be translated into bytecode directly. Then, so this is the first layer. Then this bytecode is actually translated into something else, okay, which could be optimized furtherly and furtherly until the latest element. So you have to make like a scheme, which is like this. You have the llint, which is the basic bytecode translation. Then you have the base JIT, which is a first level of optimization. Then you have DFG, and then you have FTL. So there are in total 4 levels of optimization, and the fastest one is the latest. Of course, the fastest you want to go, the more things you put at risk or you put at stake. To actually give you a recap on QEMU, QEMU also works with heavily optimized code. So what they normally do is, for every function, they get the basic blocks, they get transformed into this TCG logic. The TCG is the tiny code generator of QEMU. And basically what they do is reorder the instruction in a way that is more efficient, reuse the cache as much as possible, and whatnot. And you will see how caching is actually providing a lot of issue to the JavaScript interpreter, especially when you want to do operation on something that has spurious types, okay, which is, to simply talk, an array that contains integers, doubles, strings, and objects in the same array. And we will see how this actually changes the way the interpreter looks at the memory. Okay, so this is, again, the synthesis of how we can optimize the JavaScript code. And let me tell you how this happens. So there is no real difference between a real engine and the JavaScript engine. If you think about a real engine, for example, if you have a turbo compressor, the turbo compressor will actually kick in when your revs will actually start to be above a certain threshold, okay? Or if you are in a particular gear. With JavaScript, if a function is called more than an X number of times, it will start to get optimized, because otherwise it's very slow. Now, if you think about it, is if every time there is a function that is called, I do not cache it, and I have to retranslate it. So to re-prepare every time the bytecode, and actually re-execute it on the CPU, this is actually super slow. So what they do is, okay, if there is a loop that contains the function call, and the loop limit is bigger than a certain number, they will start actually to compile the code and optimize it in such a way that it will become faster. And that's the thing here. The more you actually call some code, the hottest the path becomes, and the best optimization it gets, with some caveats that we will see. Okay? So now we will execute this demo and see how basically the optimization, and I kept here the analogy with machine tuning, with car tuning, because depending on the number of iterations for this function, we will get different outcomes from the interpreter. Okay, so let's just go into the interpreter here. Okay, so on the right side here, you have the Docker image, and on the right side, there is the code that was appearing on the slides. Okay. So the idea here is we can call the interpreter, and as I said, you can also, if you actually grab for CMake, I did a couple of compilations. You can use the other sanitizer. Possibly this makes the jitter crash over and over again. So the cleanest is this one, which is still a debug build, but it doesn't include the other sanitizer. Plus, you don't really need it for this example. Okay, so in this case, we have in WebKit build interactive, which is the one that I. So this is actually a JavaScript interpreter, and as you can see, there are already some optimization for some built-in functions. Okay, so now we have here the prompt of the interpreter, and let's define this simple function. Okay, so this simple function is just getting an input and basically adding a number to this input. Okay, so we define the function, and for now, this is just ll int as a kind of optimizer. Okay, so if you go into, if you loop it 4 times, you still get ll int. Okay, so nothing really changed. If you call it 10 times, nothing yet changed. Now, if we go into 100 times, which is an order of magnitude above, you start to see something different. And actually, this one, the fix up everything, is actually the next level of optimization, which is the baseline jitter. And then if we go into 1000, okay, and we can go even above, I mean, it doesn't really matter. And you see that it somehow crashed. It's not super stable, and I mean, this is something that is not actually perfectly made for Linux. It works, but okay, you see that now, and I can see it here, we reach the top. We reach the most advanced optimization because here there are annotations which look like an intermediate advanced language, like LLVM, YAR, or something like that. And if you actually get it into the, definition, into the call, you'll see that, I mean, here there is an analysis, and that's the DFG, for example. So we already got into the 3rd level of optimization, which is pretty advanced as they look at the blocks, the predecessors, successors. So there is an insightful analysis that a compiler would do. Now, the example that I had in mind to actually show you what is happening, and to actually show you that it's not so arcane, It's an exercise with Binary Ninja. And the reason why I want to show you this, it's because it's exactly the same thing, but in reverse. Binary Ninja offers different representations for the code, and that's how manually an interpreter or compiler would actually work in reverse. So it would transform the source code in assembly, that's the assembly, and then it would go through different intermediate representations. So here Binary Ninja has a low-level intermediate language, medium level, and basically high level until here it gets to pseudo C. For us, the JavaScript interpreter just does the opposite, right? It gets the JavaScript code, it gets into bytecode, which could be something like pseudo C, and then it goes into deeper levels depending on the level of optimizations, right? Until it gets basically very optimized, and it looks like assembly for the CPU. Okay, so I hope I made my point. This was just a test program to tell you how the intermediate representations work. And let's go back to the Docker to actually check how this continues. So here we are still into this. I'm going to actually exit and enter again. Let me just also disable the environment variable so that we are not full of useless output. So the thing is, you can define an object like this, and you can use describe to actually get the type. Okay, now let's make it more complex. For example, B, it could be this kind of stuff, which is an empty object, and you will get some information here and some structure ID, which is normally a sequential identifier. Okay, so let's actually make it a little bit funnier, which could be, I don't know, an object, an object which may contain a property which is a string, for example. We may have made a mistake, possibly. Anyways, let's use this notation. It doesn't really matter. Okay, let's use an array and let's put integers. Okay, and C will be an array with int 32. If you then define D and contains, for example, this kind of numbers, and then you do describe of D, you get, sorry, wrong parentheses, you will get an array with double. But the surprise here comes when you define something like this, as we actually mentioned at the beginning. So imagine you have an array contains integers, an array contains doubles, an array contains eventually a string and an empty object, for example. Now, if I do describe of E, the type of the array changed to be an array with contiguous. Okay, you see also that the structure IDs are sequential, 97, 98, 99. Now, what's the thing here? The thing here is we are changing the lenses. We are changing the way we are looking at this type of data, because if you are aware of, in this case of C, they are all integers, then you somehow will look at them in this way. If you know there are only doubles, you look at it in this way. But if there are several types of objects, you need somehow to give some trust to the structure and you use array with contiguous, which basically means contiguous memory. Okay, so the way we are looking at this thing is now it's an array with contiguous memory. So let's go back for a second to our slides. And what does it mean, really? It means that we are getting into other optimizations. If you have an array with several types, the interpreter is optimizing here because, you know, it could actually create an array of integers, then create another of double, then create another of strings, and then create another with objects, and somehow make them look to you as they are the same object. And it doesn't look like they have done this thing. What they have done is just and exclusively created an array with contiguous, which is a particular structure of JavaScript. Okay, let me just close Banana Ninja as this was just an example. Okay, so now it's pretty well known right now after all those vulnerabilities, Spectre, Meltdown. When you do CPU optimization with speculative execution, you do some assumptions, and these assumptions may actually, in the end, create an issue. Okay, so what the JavaScript interpreter does is also doing some assumptions on types. Okay, when you have a loop executing 10,000 times, the interpreter will actually try to optimize, as any CPU will try to optimize. Okay, so CPUs have technologies. I mean, what I'm calling now a branch predictor is not a really new technology, but they also try to predict where a branch is trying to go. Okay, because it's somehow the fastest path or the more probabilistic path. Or if you have, for example, an AND condition, which is in an if, and the second part of the AND clause is false, the CPU already optimizes it and destroys the conditional, as that is an unconditional jump. Do you get what I mean, right? So there are optimizations which could be done from, at the compiler when you compile the code. Some others could be done when you execute them on the hardware and whatnot. The Java virtual machine, of course, is a machine in itself. So that's the power of it. You have control over everything. You have written the high-level language. You have written the interpreter in C++. And now it's up to you to decide where to optimize. So to give you an idea, JavaScript works in the browser to give to the user realistic experience, to make the web page look like it's dynamic. So the idea is actually to optimize those kind of experiences. So one of the issues that JavaScript has, and this is like one of the vulnerabilities we are trying to look at today, is a type mismatch. Okay, so there is a path that during the execution will actually make the interpreter believe he is looking at a particular type of data, but in reality is looking at a pointer. And this pointer is actually the address of the object that we are actually manipulating. Okay, so that's actually the idea. So to give you somehow an high-level example, you may have this kind of array, okay? And when you push an element, the execution in assembly may look like this, okay? Now, assembly do not have any knowledge about types, okay? If we think about C or C++, the basic types, which is double, which is int, long int, they are very tight into the architecture. You know that the char is the smallest register you could have on an x86 machine. 4 bytes, which is the right half of AIX, sorry, which is AL. Okay, so AIX is the 32-bit version. Then you divide it into 2 shorts, which is 16. AX is called, and then the half of that is called AL. So you have AL, it's a char, AX is a short, AIX is an int 32 bits and RAX is 64. So these are the basic types the CPU understands. And then you may have a long int that may actually get 2 registers. And for doubles, you may have some other optimization that the compiler will do. But low-level languages basically have type logics which are really tied into the hardware. Okay, so now let's understand why the JavaScript interpreter does optimization, but also what are the measures and the countermeasures that the interpreter has. Okay, so imagine our random function here that is still doing the same thing, right? You get a number, and this number somehow is interacted with the function. Now, the problem is what happens if instead of passing a number, you pass an object, okay? So the optimizer would actually raise a flag and say, hey, wait. This is not something that I can optimize. So there are actually some measures to avoid that. And to give you an idea, let me just show you here what I mean. There is a function which is called clobberword that our interpreter is actually calling every time. Okay, so this function is actually pending right now, and you would call an evil function which just returns 42, and then you have a function test. This test is summing a number and returns this, and then during another for loop which executes 5,000 times, you call the test function. Okay, so if you actually start this, you will see that we have hit a breakpoint, and the breakpoint is clobberword. Clobberword is actually a function that breaks JIT optimization. Okay, so this means that for this particular code that we have seen here, let me just revamp on the slides. Okay, what happens is, hey, it finds out you are sending an object in and is not doing any optimization because it thinks and it knows the types are spurious. So it says, hey, bye-bye. I'm not going to do anything more because you are trying to fool me, or I don't know what is happening. I'm not 100% sure of the types of the data that I'm using. So I'll just bail out of optimization and I do clobbering. Clobbering means clean out the structure or mark them as tainted and do not do optimization. Now, let's actually look at somehow the vulnerability we will look at today. Okay, so there are two elements in this vulnerability. One is this thing, which is the Y, which means sticky irregular expression. We'll see what it is in a second. And the other one is the last index property. Okay, the last index means it's really tied into the Y attribute. It means start to match the regular expression from the last index. The Y means read last index and start to match from there. So let's execute this code into an interpreter that I have here. Okay, this is pretty good. We can do like this. Okay, so the first gets into null, and the second it says var name. Let's look at it. Okay, so you set the last index into 3, and the strings contains 0, 1, 2, 3, so it's an empty space and returns null. But then if you go into the next one, it will return var name because basically our string contains let space var name, and you have this match, which means word. Okay, so a word with a little bit of greediness. So till the end, for example, till the next space. So that's the idea of the regular expression. Now, the thing is, what happens if I give to last index an object and I keep this sticky property? And that's where the vulnerability is actually happening, the vulnerability we will look at today. Okay, so keep in mind these two concepts. We have the sticky regular expression, and we have the last index, which is an object that the regular expression itself contains. It's like a property that is tied to the y here, which means sticky. Okay, it's just an index that says start strictly from the index that I tell you. Okay, so we have set a little bit the stage for this. Okay, so let me actually introduce you for a second before we enter the explanation of the primitive. Let me introduce a small implementation of just that part of the interpreter, how it can look like. Okay, so imagine we have a classical C structure that would represent an object of our JavaScript that runs on top. So you have a type, which is, it could be just 3 in this case, a small integer, a double, and an object. And then you have a struct, which represents a value and contains an annotation, which will tell you how to read the type, and then it contains a union. Do you know how a union works in C? If you don't, basically they get the size of the biggest element. So the union will be 64 bits in size. But depending on the name you actually give it, it will be interpreted either as an int32, a double, a void stack pointer, or an int64. Okay? So the good thing about a union is that it actually saves a lot of space, because it will not take 32 plus 64 of a double, 64 of a void star if we are on x86 64 bits, plus 64 bits integer. Okay. Then what you would do is, okay, you have also another state, which is should I optimize or not? And the optimization may be decided on how many times you execute a loop. Okay, and you start with these global variables, which says is not optimized. Okay, and then you have some examples. You can create a structure which contains a small integer, a double, or a void pointer. Okay, now what would happen if you could actually corrupt? If you have an integer, but you read it as a double, it will actually change the representation of it, but the data would be the same. Okay, so now think about this thing. We may actually set a struct and a type which contains a small integer value, as you do here. For example, you can initialize it, but then if you provide the wrong type information, you could display it in the wrong way. Okay, and this is an example. Like, you can add the value 1 to a type and decide to optimize it based on the number of call counts that you have. Okay, so if you are smaller than 100, you will basically check all the types. Okay, and you will keep the JIT unoptimized. But then if the call count exceeds 100, you basically enter into the JIT and you can decide to optimize it. So that's where the switch happens, and you basically take for granted the last type that you have seen interpreting the data. For example, that is a small integer, because before the last one that you have seen is a small integer, but basically you add a double. Okay, this is made up, but in reality, I want to show you how it actually happens to work. Okay, so this is the C implementation. Okay, so basically this is happening multiple times. So we execute this in order to trigger the jitter. Okay, so in order to set the path to be hot, That's exactly what happens in JavaScript, okay? You basically execute a function over and over again until you get into the switch, okay? Until you get into 95 plus 5, okay? It gets into the optimizer. And that's exactly what we have seen before. So what happens then is it goes into this, and the side effect is, okay, this data, if you look at it from as a pointer, that's the representation. If you look at it as a number, it's 1.337, and the type is double. So now this is a similar regex.match side effect, okay? The idea is that we may add the number 1. Imagine you start with an element, it's a small integer, and the value is possibly 0, initialized to 0. And when you get into this, you get a weird result, which is this number. So the JIT assumed that the type was double and removed any type checking. Okay, so the type was corrupted, and basically you you get the bits interpreted as a double, while you had basically something that was a small integer. Okay, that's the first kind of side effect or corruption that you can have. And another one is basically, this is very similar to the regular expression, which is, okay, you have some data pointed at one address, and this address contains a pointer, and the same bits, if you look at them as a double, their value is 0. Okay, again, you do all the hot path here, the fast path, to get into the jitter. The jitter will introduce some optimizations, and basically is assuming that the type is 1. Okay, so it's optimized for double, and the result is 1, but basically it treated a pointer to be a double, and basically you added 1 to a double, but then you dereferenced it as a pointer, and that's where weird stuff may happen. Okay, so I prepared this code that is both in C and C++ with this kind of logic, because I want to show you somehow a simplistic view on the convoluted part of the JavaScript interpreter. But now we are transitioning in how we can write the primitive of addressOf precisely for this reason. Okay, so let me just open again Visual Studio. Yes, this one. Okay, so as I said, you have the Docker image available, so that's important. So you could test how to clobber the functions. As I said, the clobber is a kind of protection that the engine would actually adopt if you're trying to optimize. So the initial exploit code looked like this, and it was full of stuff. So you had an array of doubles, then you had a sticky regular expression, and then you try to call it over and over again. And this looks really a little bit convoluted. So after looking at the code, I actually changed it a little bit, and this is the final result. So let's look at it. Let's try to understand how this works, okay? The idea is exploiting this mismatch of types, because you get into the DFG optimizer by using this kind of stuff, okay? So you have an array of doubles, and you have a regular expression which is sticky, okay? This is where the bug is actually triggering. You have a sticky regular expression, and what you do is basically you will set the last index property, okay, to a function. You could use value of or to string, okay? It's like a casting that the JavaScript is doing. And what happens is there are 3 things happening. The last index, we know, will trigger the regular expression to happen on a particular point of the string we are trying to match. The problem is this is an object. This is not actually an index. So the problem is last index is an object, okay? And it's actually a function that is returning a string in this case. Okay, so the last index of the regular expression here is set as an object, and it will return this value, which is array. Okay, and array is actually the address of this, and the way it will return this value is through a double. Okay, so let's actually make a test like this. Okay, so let's try to understand a little bit in detail what is going on. So we created an object, and it's actually giving me back this value. Okay, do you remember that our first array here, which is a kind of a global, is an array of doubles? Okay. So possibly this should be like this, right? And then we put the number here. Okay, and then we'll do unpack, and we use Q, and we use pack, and we say X. Okay. Let me see. Sorry. Pack is a tuple, so we need to give the first element. Let me check if I did everything correctly. This is not a tuple. The tuple is actually here. Oh, sorry. The element returned by struct unpack is here, and so this double number is actually corresponding to the address of the object. Okay, so this is a linked pointer, because JavaScript is not supposed to actually give you the memory address of an object. What does it mean? Now this is the first primitive, which will leak the address of an object. Then you need basically some stuff to translate it, because it doesn't really look well like this. Now the funny thing is that you will be able to rewrite this value, make them actually craft them for your own disposal, and obtain either writing primitives or reading primitives, arbitrary read and write in the JavaScript interpreter. So there are a couple of techniques that I have been developed, that I've seen developed, sorry, with these primitives. One is, since you can write everywhere, what he did was actually disabling the same origin check. That's Niklas, for example, in the example exploit that he has. He basically finds the structure and says everything is the same origin. What happens if you modify a browser like this? While you're navigating a web page, you could read the cookies of all the others, and that's super dangerous. This is like a universal cross-site scripting. Or, for example, you could try to do something else, which is executing a shell, or, still you need to do some other stuff if you are in the context of the browser, because there will be a sandbox, so you need also to overcome that. So this is like the first step, and I wanted at least to divide it into 3 or 4 different lessons, because it's convoluted. So this is like the first step, explaining the interpreter, explaining the primitives, and getting into the first one, which is just leaking a pointer. Of course, every time you try to allocate a new object, and I'm using here the describe to just match and be sure that the address is actually a correct leaked address. Every time it changes a little bit from an offset, so you could just, I had a program somewhere I will share it when I prepare, when I finalize the Docker, but you see here you have 776 F192 B0080. So this actually is another address. Okay, so let's just have a final look on the primitive exploit. Okay, so we start with an array of double, and we have this particular regular expression which will benefit from the last index because it contains the Y flag, which is the sticky. We know that. Then we have this add getter, which is a function. It gets our array as an input. It does the matching of the regular expression on a random string that I put in here and returns the first value of the array. Okay. Then, careful, what we do is we force optimization. Okay. So you can decide based on the number of iteration, okay, and in the original exploit it was 100,000. With 100,000 you will call the faster than light optimization, but we need just DFG, which is like the third level of optimization in JavaScript. And then you need to set up, so here we just say, hey, this function for you, dear interpreter, you need to optimize it, okay? That's basically what we are doing with this. And the function is here. It's just returning the first element of the array. So that's pretty straightforward, okay? So here, what we are doing is we are setting the last index property of the regular expression, which is a matching property, like saying your last index should be a number, and that's what they would actually check in the patch, but it's a function, okay? And if you look at it, what it does, it basically uses the value of, in this case, you can also call toString. It sets a value into the position here of the array and returns a string with 0. Okay, so, and then basically returns a call to this function. So the idea is when this function is called 10,000 times, at some point when the optimization happens, this value that will be returned is the first element read as a, you know that the first element of the array, it's also a pointer to the array itself in C and in C++. Okay, if you look at it as a pointer, it also points to the start of the structure. Okay, so the thing here is, instead of actually getting the value, what we are getting is, you see that val here is the object that we want to obtain the address. Okay, so in this case, this is an empty object. And what we are doing is, by doing this on line 24, that's how we leak the address. What I mean is that, I mean, you could use another object here. It could be a string, and it may actually work properly. Okay, so A and A, and then we will call it back again. So the primitive is actually stable. What I mean is that you just call it, it's a string, it's atomic. I mean, we don't get from the describe, we don't get the address. Normally it actually gives the address, but here we have something leaked. Okay, so if you go into here, sorry. This should be the address of the string. Okay, and if you want really to make sure that this is right, like this, we could do something a little bit funnier, which is you could launch it with the with GDB. and this is going to leak another address. Okay, I think we exited, so we have no memory. For example, to give you an idea, you could do this, which is a little bit better, and we should copy all the scripts inside. Like, let me see if I can copy the primitive so I show you what do I mean, right? So let's define our object as an empty object, and you can do describe as we did at the beginning, right? Obj, and this will give us this value. Now, in order to do the leakage, we need to basically inline this primitive, put it on a single line, because this interpreter compiled for Linux does not have like proper line editing. Okay, this got in, and now the primitive is called addrof, and we have defined an object, and now I forgot completely what's the name of it. Sorry, obj. Okay, so describe obj, and obj has this address. Now if I call my primitive, which is addrof obj, it will give me back a double. This double has actually a real address. Okay, now our object is empty, so whatever, we are not seeing anything. But if you are faithful for a second, we can actually do better. So obj.a equals x41, for example. Now the address possibly didn't change. If I do Control C, oops, sorry. Now this looks better. And now we can do run. Now we have the interpreter. Now we do obj equal tuck. Describe obj. So we are running inside a debugger. Now we know this code is actually well suited for this. So we can call addrof obj, and this will return a double, and it actually didn't bail out of the interpreter, which is really good. And we have the translation. You see that the threads are actually executing behind, and we know that this is the address. So for example, you can inspect this. It bail out again. I mean, the idea is that you can inspect the values, but there is something in here that makes it somehow crash or something weird. But the idea is that you can inspect it. I have to check if there is something going on with the debugger. Possibly I was too slow, which is still a possibility. Once you do Control C, it's a little bit weird what happens. I mean, I have seen executing it on Mac OS, and it's more stable, but nevertheless, that's the idea. Okay, I mean, if you don't do Control C, the interpreter will continue working without any issue. So let's do this. Obj empty obj dot a. Okay, so let's actually do like this because it's better to me. It will be faster. We know that. Sorry, describe obj. Okay, we know already that. Let me prepare here the GDB command because I have to investigate. I have to investigate why it's bailing out when I do Control C. It could be for a keyboard interrupt or something like this. Okay, so you see here, and now the thing is, if I continue and it goes back into the interpreter, that's a great question. You can actually see that the leaked address is actually this one, I mean, because we know we have the primitive. Okay, so In the ideal world, when you continue, it goes back into the prompt, but here it exits. I mean, this is a Linux version of this thing, which is not very, very stable, but you can see that the idea is that now we are able to leak an address, and that's the most important thing. Then we will continue, hopefully for the next class in a couple of weeks, I'll be able to fix this small hiccup, so we will have a complete debugging harness. Okay, and in the next class, we will look at the opposite of addrof, which is fake object, which is basically crafting an object. Thanks.